Hey everyone, and welcome to the Retro Channel. This is a follow-on from the CoCo S video mod. Today we're going to look at a CoCo component video mod. So again, I've built this on a little bit of perf board, and I've tried to do it without having to cut any holes in the case, even though this case already had a big whopping hole there, but I'm going to try and patch that up and respray it in the future, so I won't worry about that right now. So once again, it's on a bit of perf board. I'll put the schematics in the description down below. It's kind of hard to build one of these on a PCB because A, I'd probably suck at doing it, and B, the CoCo1 and 2 can have a different spot for the RF modulator, so some of them are mounted vertically, some of them are horizontal, and some people might not want to replace the RF modulator. I mean, you can still leave it in with this mod. But yeah, I've chosen to remove the whole lot, including the switch. And that's given me room for a little TRS jack, which connects to a breakout connector. So you've got your component Luma and PB and PR. And these come with a lot of flat panel displays these days. So chances are you might already have one of these. And for the audio, I've just put an RCA connector and I've got a Y splitter attached there. What I want to do today is have a look at what the Luma signal looks like on an oscilloscope, because that part of the circuit is common to both the S video mod and the component video mod. I won't go into too much detail about what we're looking at, just enough so you can sort of get an understanding of what we're looking at. If you really want a in-depth look at video signals on an oscilloscope, check out Bob from RetroRGB and Steve from TheRetroChannel. They sat down a couple of years ago and really fleshed out all the different video signals for both RGB and component video. So I'll link them up there somewhere and also in the description. So yeah, the composite video looks pretty rough. Then we've got the S video, which is a definite improvement, but I think it may need a small value resistor in the chroma output stage, because I'm getting sort of a checkerboard pattern, which may be due to too much chroma information. And obviously we've got the component video, which to me looks the best, but I guess your mileage may vary. So yeah, without further ado, let's have a look on the oscilloscope. Oh, one other thing I should mention, the alternatives, there is the CoCo VGA, which has been around for quite a while, that can output VGA from your CoCo, and also the RGB to HDMI mod now works with the CoCo as well. So there are other options. I guess this is sort of more if you're comfortable or want to build your own circuit. Yeah, this is an alternative option for you. But the other two options probably result in a crisper video output, to be perfectly honest. Anyway, let's have a look at this on the oscilloscope. Right, so what I've currently got on the display is our color bar pattern, which comes from one of the old CoCo manuals. So it's not your standard color bars where the luminance decreases, so it starts from white and ends up at blue. This one starts at green and ends up at orange, so it's not the ideal color bar pattern, but it'll work for our purposes. What we're looking at on the scope is our Luma signal plus our sync signal, and this is what's being output to the display. So this is one line of video information. So as a CRT would draw across the screen horizontally, this is one line of it drawing basically. Starting over here is our horizontal blanking. So this is basically just black, and it's not actually part of the visible display. And jumping up here is where the actual border of the screen is. So you can see that all around our color bars there's actually a sort of a dark gray border. So the CoCo doesn't output a completely black border, at least not in this video mode. It's actually like a dark gray, so it is above this, which is what we would consider to be our black level. Moving on from there, it suddenly jumps up and this is our green color bar. So that gets displayed for a certain amount of time, and then it goes up to our yellow. The luminance drops back down for blue and red because they're not as bright as green or yellow. And then we've got, this is what they call our buff color. So it's not full white, it's actually quite a bit under whitest white. And then cyan, magenta and orange are all mixed in here, and they're all the same level of luminance. And then it drops down, and that's our right hand side border and our right hand side horizontal blanking. This part here is our sync. So on a component video, the sync is mixed in with the Luma, as it is with S video and composite video. The sync is always mixed in with the Luma signal. Usually on RGB it's separate, which is why you have sync separators and sync strippers, but here it's expected to be mixed in with the Luma. And what's happening at this part where it dips down here is actually our sync tip. This would tell in a CRT display to turn off the electron gun, move it back to the left hand side of the screen, and then turn it back on, and we'd start again from here. So we'd start displaying left to right our video information as it scans across the screen. So that's the basic idea of what we're looking at. I won't go into the vertical blanking and retrace because it's not really necessary to look at the moment. Like I said, you can check out the retro RGB videos if you're interested in what all that kind of thing looks like. So that's what we want to send to the display. That's what's currently being sent to the display. But what's actually being output directly from the CoCo looks quite a bit different. So let's take a look at that. Oh, and I should mention that while we've got this up on the screen, it's also important to have the right voltages. So ideally our horizontal sync from the sync tip to the horizontal blanking should be 300 millivolts, and we're getting 280, so it's close enough. The CoCo itself is not outputting anything close to that, so that's what half of this circuit is doing, is actually setting that up correctly. The other half is, once I bring it up on the display, right, so this yellow part is still what's being output to the display, but this is the same signal that's currently being output by the CoCo. So you'll notice something looks very different about this signal. It is basically a mirror image of what's being sent to our display. So the CoCo outputs an inverted Luma and sync signal. And if you were to send that to a display, it would have no idea what to do with it, because it would treat these brightest areas, so this is our yellow and white color bars, it would try and treat them as probably horizontal sync, but because there's two of them close together, it wouldn't make any sense, and yeah, the display wouldn't be able to lock on to the horizontal sync. So this is what the other half of our circuit is doing. So we're inverting this signal with the BC557 transistor, and the resistors that are around it are basically just setting up our correct voltage levels. So if we were to bring the cursors back up and take a look at the second channel, and remember that this is inverted, so we want to look between this point here, which is our sync tip, and this, which is our horizontal blanking. It's only 200 millivolts peak to peak, whereas we want something that's either on or close to 300. So again, even if we just inverted this and sent that to the display, it probably wouldn't look right. You'd probably lose brightness information, or possibly it wouldn't be able to lock onto that sync tip. So that's why there's, you know, 4 resistors and that transistor in that little part of the circuit, because we're setting up the correct voltage levels and also inverting that signal. The other transistor in the circuit is basically just a buffer. So if we were to try and drive our display from the emitter side of that 557, it probably wouldn't have enough current to actually drive the display. So the second transistor, the 2N2222, is basically just acting as a buffer. And that's pretty much what's happening with the S-Video chroma signal. So you'll see that we've got a 2N2222 set up in a similar configuration. So it's just buffering that signal so we don't try and pull too much current directly off one of these chips, because it either just won't work, or we'll end up burning out something inside, or the chip will shut down. So yeah, the Luma is 90% of this battle is getting this correct to feed to the display, especially this horizontal sync tip. The color information, so the chroma with the S-Video mod, or this UV, or the blue-red from the YUV mod, is pretty simple to set up. There's not too many components involved, as you can probably see. Well, the blue Luma difference and the red Luma difference, we'll bring those up on the scope just so you can see the relationship between all these different signals. Okay, so here's our 3 signals. So we've got our Luma in the middle, and these top and bottom ones are our 2 color different signals. So this is our red Luma difference, and this is our blue Luma difference. So this would be the blue plug and the red plug, and that's the green plug in a component video setup. So ignore these different colors here, it's just because I ran out of cables, but we've got our blue, red, green. For those keen-eyed viewers, this is a 2-channel oscilloscope, and I've got 3 signals on here, 3 waveforms. This is just saved as a reference waveform, so that's why it's cut off the edges, but it's a little cheat to be able to have 3 waveforms on the screen. So this is just saved in memory. It's not actually being fed into the oscilloscope anymore. Anyway, so what we can see is, again, this is our sync tip, our horizontal blanking. This is the screen border. So both of these two, I actually don't know what that little drop is there, but both of these two should have no color information. So they're basically flat. The U and V in component video sits around 0 volts DC. So this is at 0 volts, and it goes from minus 350 to plus 350 millivolts. So it has 700 millivolts peak to peak, whereas our Luma and sync, the actual Luma part is 700 millivolts peak to peak, but if you add the sync in, which is another 300 millivolts, you get 1 volt peak to peak. Coming in, there's no color information. Ignore this little mess down here until we get to what is our green bar. So you'll remember that it jumps up here. This is where the green color bar is, and you can see this part. Oh, both of these color different signals actually drop down, but when we go to the yellow bar, our luminance picks up because it's brighter than green. This one returns back to basically 0, so there's no color information here, but this one stays low. So that all 3 together form our yellow color bar basically, and it continues on from there. So blue and red have little luminance information, but you can see the difference between this one here goes to its high point, this one stays mid, that goes high, that goes mid, so on and so forth. So finally, we'll just have a quick look at the board, and I'll explain why the NTSC and PAL versions are different and how we can use this to take advantage of both variations. Hey, it's future me. So a couple of things that I forgot to mention. The difference between the PAL and the NTSC CoCos. Because the 6847 video chip was designed for NTSC, the PAL variants actually have to insert more horizontal lines into the image. And there's also obviously frequency differences. So there are some extra components in the PAL versions, but unfortunately I can't find a PAL CoCo1 schematic to actually show what those differences are. And that's why we tap from the 1372, the Luma input of the mixer chip for the PAL variants, and you'll see for the NTSC variants, we just tap directly from the 6847, its Luma output. The other thing I wanted to mention was the video signals coming out of this circuit are not within spec. Usually you'd have a sync tip clamp that clamps the sync tip to minus 300 volts, and then you've got your blanking level at 0 and your luminance information up to 700 millivolts. This circuit doesn't include that because I want to keep it as simple as possible, and to be honest, most displays aren't fussed by it. There's only a minor DC offset to that signal. And likewise with the U and V color signals, again, normally they'd center around 0 volts and go up to 350 and minus 350 millivolts. They also have a DC offset, so they sit just above 0 volts and do their thing. I did try and AC couple those, but what actually happened was it did remove the DC offset, but anything that dropped below 0 volts, it basically sliced it off at about minus 100 millivolts. So that didn't really work out. And again, to be honest, the displays that I've tested it on don't seem to be fussed by the small DC offset. I know one of my displays, the dark gray border around the image actually shows up slightly blue, but it doesn't do that on other displays. So I can't really explain what's going on there, but once again, I want to keep the circuit as simple as possible. So it wasn't a big deal for me, but just something to keep in mind. So yeah, carry on. So here's the board that I knocked up. If you're handy with a soldering iron, pick up a little bit of perf board and you should be able to build this. I mean, I know it looks a little bit daunting, but it's actually not that tricky. Once you sort of lay out in your mind how the schematic is going to sit on this little circuit board, you should be fine. But as I said, because some people might not want to replace their RF modulator, actually replaced so the whole RF modulator and the channel select switch. So this takes up the room of both of them, but that works because this is where the channel select switch would be, which has a nice little hole in the case, and this is where the RF modulator would be, which also has a slightly bigger hole. So that's why I sort of chose to do it this way. But the CoCo2s, some of them have a vertically mounted RF modulator, so it's not going to work the same if I, had a PCB made up. The channel select switch and the RF modulator sit in different places, so it's not one size fits all, unfortunately. For PAL, you can tap Luma off pin 9 of the 1372, which is actually the Luma input to this mixer chip. And for the U and V components, we tap that off pin 10 and 11 of the 6847 and pretty much just ignore everything else. For the NTSC models, things are actually possibly a little bit simpler because we don't have to worry about inserting extra lines for the actual image. Everything's tapped off the 6847. So Luma would come off pin 28. And again, our color difference signals come off pin 10 and 11. So this should work for the CoCo1 and the CoCo2 in NTSC land, which is kind of handy because the CoCo2 for NTSC is very hard even just to composite mod it. So this could be the way to go. The other option is the RGB to HDMI mod, which Aaron from Retro Hatch Shack showed off in a recent video for the CoCo1, but that should also work for CoCo2s as well. So that's an all digital mod using a Raspberry Pi Zero that was originally designed for, I think, the BBC Micro, and it's been adapted for various 8-bit computers, and even the Amiga recently got a version of it as well. So that's good if you're looking for an all-digital solution. You've got just HDMI out, you've still got to route audio out, because the RGB to HDMI just does video, it doesn't do any audio. But yeah, here we're kicking it old school, so we've got all analog outputs, which is good for a CRT. HDMI is obviously a lot easier to connect to a flat panel. Yeah, anyway, as I said, for PAL models, we can tap Luma and sync off the 1372. For NTSC models, we just tap Luma and sync off pin 28 of the 6847, and our color difference signals come from pin 10 and 11. And in theory, that should all work. The only other thing going on here is the audio, which is coming from pin 3 of the RF modulator and just being attenuated a little bit by these two, and just being output. Obviously it's mono, but I've got a Y splitter to split that into dual mono for the receiver that it's currently connected to. Oh, one more thing I should mention, the Dragon 32, for those in the Europe and the UK, I don't think this will work with the Dragon 32, at least not in this configuration. It uses a different way of generating that Luma and sync from the 6847, so it's not designed to work with that. I mean, it might, but I don't have one to test, so yeah, RGB to HDMI mod might be the way to go there. Speaking of which, I will actually try out the RGB to HDMI mod in a future episode, because it's actually able to simulate those artifact colors even on PAL machines. So it'd be very interesting to see how that works on a PAL machine, and play some of those games as they were intended, with those orange and blue NTSC artifact colors being generated in a lot of games. So that'd be pretty interesting to see coming from a PAL machine, but that'll be a project for another day. So that about wraps it up for the CoCo for now. Hopefully I've explained everything that in a way that makes sense, but if not, leave me a comment down below. I'll try and answer if I can. But yeah, I think it's time to put this aside, at least for now, until we get to clean it up and fix up these holes and all this missing paint. Yeah, as always, thanks for watching the Retro Channel. I will see you again next time. If you haven't already subscribed, you know what to do. And yeah, leave me a thumbs up if you liked the video. There is still the 65XE on the project shelf. And there's also Henry, who we will talk about later. So as always, thanks for watching. See ya.